Hello everyone, I'm Pratik Biswal, a third year undergraduate student of Department of Aerospace Engineering at Kharagpur. This video is being submitted as a part of the assignment for the course Viscous Flow Theory. In this video, I'm going to derive the boundary layer equations by the asymptotic methods. The asymptotic methods, for further insights on it, I would attach a few links in the description. You can see them. Now let's proceed on to the derivation. To begin with it, we first need to see the Navier-Stokes equation. This is the Navier-Stokes equation in its non-dimensionalized form. This is the continuity equation, this is the x momentum equation, this is the y momentum equation. The variables u, v, p and the length scales have been non-dimensionalized in this manner, as I have mentioned. Here we get a 1 by Reynolds number term and we denote it by epsilon, and it will be very less than 1 when the Reynolds number is high enough. Now let's denote the partial derivatives as u subscript x, u subscript t and u subscript y as I have written here, and replace all of these assumptions in the main equations, and then we would obtain something of this sort. And then we can notice that the epsilon term gets multiplied to the highest order derivative, and we can infer from that this is a singular perturbation type problem. Now what again it is, you can probably refer to the links that I have attached below or check on the internet for that. Now this problem can be have two types of solution, that is the outer solution and the inner solution. For this case, the outer solution will be the one where the effects of viscosity would be negligible, that is the free stream, and the inner solution would be the boundary layer where the viscous effects would be predominant. Now the outer solution can be denoted by the small q, u, v and p. It has been mistakenly written as w. Now this q can be expanded as q naught epsilon alpha q1 epsilon to the power 2 alpha q2. This is how the asymptotic method expansion looks like. The continuity equation, as we know, is ux vy, and when we asymptotically expand u and v in the written manner, we would get a expression something like this. This is obtained by the analysis of the leading order terms. The leading order terms are the ones with the lowest power of epsilon. Since the lowest power over here is 0, we get the u naught derivative with x and v naught derivative with y. Now moving on to the x momentum equation, which is this one, and we substitute all the asymptotic expansions of the variables derivated with the respective quantities t, x, y, x, 2 times x and 2 times y, and then we analyze the leading order terms for all of them, and we would get something like this. All the terms with the subscript 0 that denotes the leading order term, and similar analysis for y momentum equation as well. Now if we notice carefully, this second equation, third equation and the first equation, they are nothing but the Euler equations, the equations that describe the fluid motion without considering the effects of viscosity. Now let us move on to the inner solution where the viscosity would be predominant. In this case, the y would be scaled by delta, that is the boundary layer thickness, and the other variables remain the same way. X remains as x, t remains as t, and delta would be denoted as epsilon power lambda. Now let's recall that epsilon was 1 by Reynolds number, and if we remember from the order of magnitude analysis, the boundary layer thickness was indeed dependent upon some power of Reynolds number. Now for instance, we don't really assume that power and just denote it by lambda for the time being. And then the derivatives del by del y, when scaled with the factor delta, would change to this way, and so will the second derivative. And the inner solution that's denoted by capital Q, u, v and similarly p, the same mistake here again. This is the asymptotic expansion of the q naught, and the continuity equation this time changes to something like this. And when we put the expansions for the u and v and we analyze the leading order terms, at the leading order term there will be only del v naught by del y. The leading order will be here the lowest order of epsilon, that is minus lambda. We'll get this, and then we'll get that v naught is only a function of x since it is derivative with y is 0. And then what we'll notice is that y is equal to 0, the v is equal to 0. This is nothing but the impermeable boundary condition for the flat plate. That is, the v velocity can't pass through the flat plate. So what we infer that v naught has to be identically 0 for all the points. From that, what we would get is u naught x plus v1y is equal to 0. And this indeed is true if we would recall from the order magnitude analysis that V1 was one order less than the U naught. And then coming to the x momentum equation, u of t ux 1 by delta v uy plus px epsilon uxx plus uyy 1 by delta square. And we substitute the asymptotic expansions for all the terms with their appropriate derivatives t, x, yx, double x and double y. And then we again analyze the leading order terms, and this time we assume that epsilon is equal to delta square, and hence we'd get that delta is equal to epsilon to the 1 by 2 and lambda is equal to 1 by 2, the lambda from over here. And this analysis satisfies the order of magnitude analysis that we had done previously, and delta is indeed proportional to the square root of 1 by Reynolds number. And we would get this equation as the leading order: u naught t, u naught x, v1 u naught y plus p naught x plus u naught double y. And a similar analysis for y momentum equation was done as well, but in this case the leading order term would only be this, the p term only. All other terms would be of lesser order than this, and hence we'd get that p naught y is equal to 0. Now these equations, the 4, 5 and 6 are the boundary layer equations that we have obtained over here. These equations had been first derived by Ludwig Panton and presented in his paper titled Motion of Fluids with Very Little Viscosity. This discovery of boundary layer was a very significant contribution by him, and it resolved several important paradoxes such as the D'Alembert's paradox, which said that there was zero drag when the pressure was analyzed over the flow over a cylinder. But that was not the case. There was drag due to the friction and the viscosity of the fluid, but that couldn't be found out by then. It was Prandtl who resolved that problem by proposing his idea of a very thin boundary layer near to the body over which the fluid is flowing. Well, he has indeed other contributions as well, for which I will attach another video in the description, and you can probably look for his detailed contribution to the world of aerodynamics and fluid mechanics. And for the time being, thank you for watching this video.